This is a demo of one of Semu's powerful dynamic debug features, hardware breakpoints. Why is dynamic debug so valuable for FPGA-based emulation? Well, FPGA emulation provides a huge speed up over simulation. For long simulation runs, whether that's for running regressions or trying to touch hard to hit corner cases or running real data such as video for example, FPGA emulation is a huge win in these cases, able to execute in seconds what may take hours or days to run. But the time to compile into an FPGA is longer than that for a simulator. So what's the cost of debug with FPGAs? Typically, when you're working with FPGAs and doing debug, each debug iteration can require re-instrumentation and resynthesis. That makes each debug cycle take hours to days, which bogs down problem diagnosis and resolution. With Semu, you get dynamic debug. You can dynamically instrument on the fly, immediately and directly while working in FPGA-based emulation. Semu gives you full visibility into all of the register state in the design, in the FPGA at any time. And you can set complex breakpoints against this register set. No need to recompile, avoiding re-instrumentation and resynthesis. So you get debug iterations in minutes, not hours or days, and you can resolve problems quickly. In the demo, we're going to see a DMA subsystem running in Semu. It consists of a DMA controller, memory, and interconnect running inside the FPGA, and it's connected to a C-based test bench in the host, which includes a Tickle GUI to control it. The user can use the test bench GUI to configure DMA transactions, to read and write memory, and of course the DMA controller will move memory when commanded. We'll be working with a 32-bit counter that's sitting inside of the DMA controller. That counter iteratively counts from 0 to 1000 and back. And we'll also be looking at a FIFO interface that is on the DMA controller's interface to memory. Let's look at the demo. We're going to start off by opening our project inside of the Semu window GUI. So we're going to open the project, we're going to start emulation, and we're going to open up the emulation control window and the Semu instrumentation panel. Set our breakpoints live in the middle of an FPGA emulation, and then turn on instrumentation. So there we're going to select signals, open up the Semu instrumentation panel. You see the design hierarchy in the top left. We're going to find the DMA controller, add the IFC underscore count, which is a 32-bit counter, down in our bottom signal collection, and then we're going to add the FIFO interfaces. There's the DMA controller. We're going to promote that to the top, so that's what we're looking at only. On the right, when you click at that level of hierarchy, you see all the registers that you can set breakpoints against and instrument. We just added the counter. Now we're going to add the FIFO interesting signals between the DMA controller and the memory. We're going to set the counter to 1000 and add that to the A breakpoint and enable A as a breakpoint. And then we're going to turn on readback, which allows the breakpoints to be enabled, run, and we immediately stop at clock number 1000, which happens to be when the counter hits 1000. Now we're going to turn on instrumentation for that counter. And we're going to run a few more cycles and grab the signals from the data of the registers down on the FPGA dynamically. Now we're going to turn that off, turn off that breakpoint. We're going to add another breakpoint, which is when the FIFO for the interface from the DMA controller to the memory is not empty. We want to break. So we've turned on that breakpoint, and we're going to click Run again. And once we do that, we're going to run for a while because there's no DMA activity between the DMA controller and the memory. We're going to set some memory up. We're going to fill the memory and look at the memory. And then we're going to set up a DMA from the 100,000 hex to the 100,000 C0 hex. We're going to move those forwards down. And when we kick off that DMA, we should hit that breakpoint because that FIFO should get some data in it. Immediately we hit set, it stops. We've stopped it now 7 million cycles into our FPGA emulation. We're going to turn on the and look at those interface signals on that FIFO. And we're going to rerun and capture the data from that breakpoint forward for the next 2,000 cycles. We're going to run n to run 2,000 cycles. And when we turn off readback and hit run again, we'll be running at 50 megahertz. So now we're flying along off to our next interesting point, and we're able to dump memory. And you can see that the DMA activity happened. We moved those first 4 words down to the 4 words at 100,000 C0 hex. Now we're going to take a look at what we've captured. So we've captured 50 cycles after at and after the counter hit 1,000, and we captured the data from when that FIFO first went non-empty. And that's what we're going to look at first, which is way out in time. Obviously, we ran a lot of cycles before we hit that breakpoint, and we can see all that data that was in the registers at various cycles from the point that we hit the breakpoint, from the time that we turned on instrumentation, dynamically in the FPGA. And now we're going to go back and look at the interface count, which is way back in time, early on, obviously after 1,000 cycles. We hit that. So as we zoom into the first data, we should see it at 1,000. And since this counter wraps at 1,000, the next cycle it goes back to 0, then 1, 2, and then it counts up back to 1,000 again. In this Semu demo, you saw the ability to dynamically set breakpoints and turn on visibility at any point in the middle of an FPGA emulation, dynamically, without prior instrumentation, avoiding re-instrumentation, resynthesis, avoiding compiles, all dynamically, enabling iterations in minutes instead of hours and days. That's Semu. Emulation performance and simulation prices. Connect, build, and go. Ease of use gets you going in less than a day. And dynamic debugging enables iterations in minutes instead of days.